This video is an introduction to linear models. We'll take a first example and look at how we can go from the verbal or written description of the situation to a table of values, into an equation, and then into a graph. And then we'll see how, with different examples, you could start at any one of these four beginning points and figure out the other three. One concept that we will keep coming back to is that linear models are used to represent a situation where there is a constant rate of change. This constant rate of change in our first example will be the change in total cost to attend the Reggae Fest when we don't know exactly how many tickets we'll be buying. That's going to be the variable. For this problem, we can show the total cost for various numbers of tickets. Let's go with 1, 2, and 3. And in the table, we won't just put the final cost. I also want to show the calculations that we're doing. If you only buy one ticket, you'll have the $12 for parking and $20 for your ticket. Total's $32. If you're buying two tickets, you still have the $12 to park and $20 twice, for the total $52. And so 3 tickets, $12 for parking just once, and then 20 plus 20 plus 20, for the total $72. The $12 that we only ever see show up once in these calculations is the starting value. It would be the part of the cost that exists before you even buy a single ticket. And the repeated 20s are where we see this constant rate of change. We can see that the total cost to go to the Reggae Fest increases by $20 each time we buy one additional ticket. So the $20 per ticket is the constant rate of change. As we go through each example, we will pay very careful attention to the two quantities of starting value and the constant rate of change. From a table, we want to see that our output value, or the calculated value, has a constant increase or decrease. And we want to see what would that starting value be before any of those increases or decreases. In a verbal description, it's frequently pretty clear what's the one-time cost, in this case, the starting amount, and what's the variable cost. Also in this table, we can see how to construct the equation that represents the total cost to attend the Reggae Fest. We know there's a starting amount of $12, regardless of how many tickets you buy, and then there's another $20 per ticket. How many tickets are you buying would be the variable t. If t equals 1, then we have 20 times 1. If t equals 2, then we have 20 plus 20, also known as 20 times 2. 3 tickets, there's 20 plus 20 plus 20, which we would just say 20 times 3. So our variable t is representing how many tickets are being bought, and that is connected to this constant rate of change. $20 increase per ticket, we're multiplying by how many tickets, and adding it to the starting value to calculate the total cost. Finally, let's take a look at the graph of this equation. On the graph, we have the variable going horizontally on this line called the horizontal axis. The label shows it's the number of tickets. The output of this calculation, the total cost, is on the vertical axis. Remember those two key quantities for a linear model, the starting amount and the rate of change. On the graph, the starting amount is a point on the vertical axis. The starting cost, without buying any tickets, was $12. It is a point on the vertical axis, so it's called a vertical intercept. We will have a line eventually that graphs this situation, but our starting point is this point on the vertical axis called the vertical intercept. It represents the $12 starting amount to the total cost. The next point that we can plot would represent the total cost when one ticket is bought. Buying one ticket, we calculated earlier that that would raise the cost to $32. So a point right here for one ticket makes the total cost equal $32. When we plot the results of the other calculations, that 2 tickets will cost $52, 3 tickets brings the cost up to $72, these points will all form a straight line. And this line represents the graph of this situation. And this is why linear models get that name. that when graphed they form a straight line. This kind of a pattern helps make it very clear for other values that we didn't calculate. Like for 4 tickets, we can see that the total cost would be $92. So now that we've seen for this example the written description, the table, the equation, and the graph, let's switch the numbers around and see what we can do with various starting points to the situation. Can you take the information in this table and come up with the equation, a verbal description of what's going on, and make a graph for it? Let's still assume that we're talking about going to a reggae fest, and that you're looking at an upfront cost for parking, and then a variable cost based on number of tickets. The two quantities we're looking for with linear models are the starting amount and the rate of change. Now the starting amount we really don't see just yet. This $35 cost, although it's first in the table, that's with one ticket already built into the total cost. Maybe you're seeing a pattern to figure out what that starting value is just for parking with no tickets, but let's look at the rate of change first. What we're looking for in a table when it comes to a constant rate of change is looking at how our total cost is changing. Going from 1 ticket to 2 tickets meant that the cost increased by $15. So that's starting to look like $15 per 1 ticket as the rate of change. And the table doesn't give us the cost for 3 tickets or for 4 tickets, but it jumps right to 5 tickets. But there's still a way that we can come up with the rate of change. From $50 to $95 is an increase of $45. But how many tickets were in that increase? It went from 2 tickets to 5 tickets. That was an increase of 3 tickets. So the rate of that change, $45 per 3 tickets, when we talk about a constant rate of change, we're talking about this rate being a unit rate, which means the denominator doesn't have a number. Technically, it's per 1 ticket. So $45 per 3 tickets is a nice rate, but our unit rate, when we divide 45 by 3, we'll get the $15, and we can carry over the units, dollars per ticket. And now that we know the cost per ticket, we can see what that starting amount was. Taking away the $15 for the ticket will leave us with 0 tickets, and the total cost would be $20. So a verbal description of this problem could be that parking at the Reggae Fest will cost $20, and each ticket will cost $15. We also have enough information right now to construct the equation for total cost. We'll use C to represent the total cost, and that's calculated by the starting amount, parking was $20, and then it increases by what constant rate of change? $15 per ticket. The number of tickets represented by the variable t. Lastly, we can make the graph, and again we're going to use the starting amount and the rate of change, or these values that are in our table. To make the graph, we have the vertical intercept, which is the starting amount, $20. The cost without buying any tickets, or buying 0 tickets. After 1 ticket, the cost went up to $35. After 2 tickets, it was up to $50. And we did calculate, or show in the table at least, that 5 tickets cost $95. And a straight line through all those points will graph this equation. Let's try another example where you start with the equation. And the equation is C equals 10t plus 16. C equals the total cost, T equals the number of tickets. Based on what we've done so far, can you visually spot the starting amount and that constant rate of change of cost per ticket? The constant in this expression, the plus 16, would only show up once in this calculation of total cost. But 10 times t represents 10 added over and over some number of times, and the t tells us how many times. So the 16 is the starting amount, and 10 is the constant rate of change. Another way for us to get to these quantities of constant rate of change and starting amount would be for us to make the table. To create the table, it's really up to us to choose values for t. We can start small and numbers that are easy to work with, and 0 is going to help us find that starting amount. When t equals 0, that means we haven't bought any tickets, so the only cost is the cost of parking, that starting amount. The way that we'll fill in this table is to use the equation c equals 10 times t plus 16. If t equals 0, then c equals 10 times 0 plus 16. Multiplication first, 0 plus 16, so we get the result of just 16. When t equals 1, we've got 10 times 1 plus 16. 10 plus 16, 26. We can continue this process as long as we want in the table. Just be sure that the only thing that you are changing is the variable t. Everything else about this expression stays the same. 10 times t plus 16. And it would give us these results in the table. So again, when t equals 0, we'll see our starting amount, 16. And the way that we find the rate of change in a table is to look at the change in our calculated values. 16 to 26 is an increase of 10, and that happened when we bought the first ticket. Buying the second ticket, we see another increase of $10. So there's the constant rate of change, $10 per ticket. Lastly, let's take a look at this graph, and again, we'll focus on starting amount at 16. That's going to be, on the graph, the vertical intercept. And this time we'll look a little bit more closely at where we see on the graph the $10 per ticket. We know that it helps us get from one point to the next on that line, but we'll show a few more of the details about this rate of change. On the graph, we would call it the slope. On the graph, we're taking the starting amount, putting it as the vertical intercept. That starting amount in this problem was 16. $16 for parking without buying any tickets. Our table gave us these other points. One ticket brings the cost up to 26. 2 tickets up to 36. 3 tickets, 46, and so on. And a straight line through those points will give us the graph of that equation, where we could see 4 tickets would be 56, 5 tickets 66, and so on. So before we go to the last example about what to do when our given information is the graph, let's talk a little bit more about some of the details of the graph. For sure, our vertical intercept is the starting amount. So I would know already that the equation for this line, cost equals $16, and the line is going uphill, means we have an increase in cost, so I'll be adding some amount to it. Because the points are on a straight line, it means I have a constant rate of change. If I was increasing by $10 sometimes and $12 other times, different amounts, then the points just wouldn't be on a straight line. So this constant increase, the constant rate of change, which we know is the second term in this equation, we have to get from looking at the change from one point to the next on the line. We could see that 0 tickets cost 16. With 1 ticket, it went up to 26. So from there, we could see 16 up to 26. That was an increase of $10. And how many tickets change? 1 ticket. So there's a way for us to identify the rate of change from the graph. It's pretty easy if we can spot our starting amount and what happens when we set our variable equal to 1. But know that it works for any 2 points on the line. So if I looked at this point, which tells me 2 tickets will cost $36, and this point tells me that 4 tickets costs $56. The rate of change, again, we're talking about the change in our total cost. So the change in total cost was a change of $20, but that was an increase when we bought how many additional tickets, from 2 tickets up to 4. It was $20 for 2 tickets, and if we divide that into a unit rate, we'll get $10 per 1 ticket. So we see that constant rate of change an increase of $10 per ticket. So our cost equation is increasing by 10 times t, how many tickets. Now the way that we set up our rate, we always need to have this vertical amount in the numerator. So total cost per ticket. This also connects to some other terminology you might have heard called rise over run. Rise and run. It refers to these vertical and horizontal changes when you go from one point to the next. The vertical change was the change in total cost. It went from 36 up to, if you look at this point there, trace it all the way back to 56. So our rise was an increase of $20. The run is how much change horizontally did we see. We saw a change of 2 tickets up to 4 tickets. So that was a change of 2 tickets. And we always call it rise over run as a reminder to set up that vertical change in the numerator. Rise over run. Vertical change compared to horizontal change. So let me give you a fresh graph to look at, and you'll come up with the equation, a table, and a verbal description. Here's the graph for you to try working with. Actually, pause the video and give this one a try yourself. See if you can come up with the equation, make a little table, and a written description of what this graph represents. You could still use it's calculating the total cost for a Reggae Fest based on number of tickets, or you could make up some other type of event that suits you. So pause the video and try it, and then restart it, and we'll go through this problem together. So always remember that linear models are based on 2 quantities, a starting amount and a rate of change. On the graph, the vertical intercept will tell us that starting amount. It's $24, so that's how much parking is for this Reggae Fest. Next, I have to look for the rate of change. Well, it started at 24. After the first ticket, it is up to 38. That looks like an increase of $14 per ticket. The line is straight, so I really don't have to check anywhere else, but I could just because I like to do these things. So how about 4 tickets costs exactly $80? That's a nice one. So from the starting amount, which was $24, no tickets, $24. We see an increase in this cost, $56. And that took place over 4 tickets. $56 divided by 4 is going to give us the $14 per 1 ticket. So a few ways for us to find that constant rate of change, $14 per ticket. We've got enough now where we can come up with the equation for total cost. $24 was the constant, that starting amount. $14 the rate of change. So I'm using C for total cost. T is the number of tickets. There's our equation to calculate the total cost. So let's wrap it all up with a little table. Our starting amount with no tickets purchased was $24. 1 ticket got us up to $38. 2 tickets gets us up to, well, we didn't calculate that. Let's see right there, $52. And if you wanted to show the formula in this table, we could say if you wanted to be general and use t as your variable, then your cost would be, what would it be? We would just list this equation. That's the way to calculate cost, 24 plus 14t. So when the number of tickets is unknown, this expression will calculate the total cost.